So this is the first session for kinetic theory of gases, and this will be a short one. Okay, short and precise. So first, whenever we are reading gases or whenever we are studying gases, the first thing we should know is, why are we studying gases? Is there a specific reason that we are studying gases and not solids and liquids? Now I hope all of you remember that in case of gases, the distance between particles is way larger as compared to the size of the particles themselves, right? So what that implies is that if we have two spherical particles of radius r each, and if they are separated by a distance r, then their radii is way smaller than the distance between them. Okay, smaller radii and the distance between them is way larger. So this, for the considerations that you can make, is that smaller distances will be affecting this gravitational force and electrostatic force between two particles. Because why we know is that these forces are proportional to two quantities. Like for gravitational forces it's m1 into m2, and for electrostatic forces it's q1 into q2, and inversely proportional to the square of distance between them. Now since the masses themselves will be very small, plus the radii being smaller than the distance between themselves, or hence we need to use the word capital R here, sorry. So if these distances are larger, then when you are squaring large values, they'll give even larger values, right? Say if r equals to 2, then r squared is 4. But if r is equals to 10, then r squared is 100. So basically these two forces, this one and this one, will be negligible owing to the large distance between the particles. So this gravitational force or attractive force does not exist. There is no attractive potential, and in case of electrostatic force also, attractive and repulsive forces both are considered to be negligible as far as the topic concerns you. Plus, it is also assumed while studying gases that since the interactions, the attractive and the repulsive forces or attractive and repulsive potentials are minimum. Now if you are studying just one body which is not being affected by other bodies around itself, it's easier. You can basically assume the body to be independent and study it. So studying gas particles is way easier than studying solids and liquids, where a lot of other factors come into play. Now the particles are assumed to be identical, that is, they are assumed to be perfectly rigid, perfectly elastic, and they are assumed to be of identical shape, size, mass, and everything else. And there is something called mean free path, the definition of which is mentioned. Now just to introduce you, when you see a closed space, you can have a number of particles in that space, right? So what happens is that since you can have a number of particles in that space, you can have one particle, you can have another particle, you can have another, then another, and all the particles, all the gas particles are in random motion. Now during the random motion, they can collide, with each other. So we'll describe it a little bit better, but just for the basics, you can know that the average distance traveled by a gas molecule between two successive collisions is known as the mean free path. This is the formula for the mean free path, where d is the diameter of the particle and n is the number of particles. Plus, another assumption is that particles travel at high velocity. Now you just see 4 pointers marked here, but the body being rigid, the body being perfectly elastic, these two are also important considerations, and you will know why. Now for the next part, we have something known as degree of freedom. Now assume there is a plane surface on which a ball can roll or can move. Okay, it can move here, it can move here. So here you can say degree of freedom is 2. Now why is that? Let us discuss. Now as the definition mentions, degree of freedom refers to the number of coordinates required to describe the position and configuration of a system of particles. So if you take into consideration the two-dimensional plane here, or the square region here, and the small particle inside it, it can go right, it can go towards the bottom. So it can travel along the x-axis, it can travel along the negative y-axis. So if it is at a position, suppose say if it moves to this point. Now this point can be described as point P, which has some value of x and some value of P. It can be denoted by using two coordinates, the x coordinate, the y coordinate. Similarly, if there is a cube, okay, a cube can have 3 axes. Say this is the y axis, this is the x axis, and this is the z axis. And if we have a particle at any point, the position of the particle P can be denoted by x, y, and z. So to represent the position of the particle in here, we need two distinct coordinates, x and y, which are perpendicular to each other and independent of each other. Since the position or displacement can change along x or y, the velocities will also have x component and y component. The acceleration will also have x component and y component. And keep in mind, the x components are independent of the y components and the y components are independent of the x components. So hence we need two coordinates x and y to describe its motion in this plane, and hence the degree of freedom is 2. In this case, in the three-dimensional case, we need x, y, z for position coordinates. For velocity coordinates also we can have vx, vy, vz. Okay. And for acceleration coordinates we can have ax, ay, az. So here the degree of freedom is 3. Here the degree of freedom is 2. So simply putting, the number of coordinates which you can use to denote the position, velocity and acceleration of the particle, that is the degree of freedom. So degree of freedom can be denoted by a formula, that is dN minus R. So you people are mostly gonna be dealing with up to 3 dimensions. So D, you can take 3 if you have a 3-dimensional motion in consideration. That is X, Y and Z axis are present. Or just like the cube that we discussed with the degree of freedom 3. Now let's take the example of that cube itself. There was this cube that you had. There is a particle inside it. So the number of dimensions is 3. The number of particles, say we have one atom, so it's a monoatomic particle. And is one of these planes or one of these axes blocked for travel? No, it can go along any of the axes. So degree of freedom is 3 into 1 minus 0. So degree of freedom is 3. Okay. We'll be discussing it in a moment. So just know degree of freedom is equals to dn minus r. Or for you people, the formula that is used is 3n minus r. D is the number of dimensions, n is the number of particles, r is the degree of okay, my bad. R is not the degree of freedom. R is the number of constraints. Okay. You will have certain cases of monoatomic, diatomic and triatomic molecules that we'll be discussing just in a minute. So constraints, that is one important aspect, whatever you had as R in the last page, number of constraints. So constraints can be described as the number of restrictions that exist for the motion of a particle. Say you have a 2-dimensional plane and you have a sphere, you have a ball, and you say that the ball can only move along this direction. ये यहाँ नहीं जा सकता. So basically its x-axis motion is restricted. It can only move along the negative y-axis, or if you prefer negative and positive y-axis, it can only move along the y-axis, plus minus y. So that means we impose a restriction on it and prevent it from going along the x-axis. So R is 1. For better measures, let us first see the very simple aspects. Now when there is a monoatomic molecule or a single particle, there are 0 constraints on it. It can go along the x-axis, it can go along the y-axis, and it can go along the z-axis also. If we have diatomic particles, there is 1 constraint on the system. Okay. If we have triatomic setup, there is a linear and there is a non-linear case. For linear cases, you have 2 constraints, and for non-linear cases, you have got 3 constraints. Okay. The number of restrictions imposed on their motion refers to a constraint. Now let us head back to this topic, the degrees of freedom. Okay, let us calculate all the degrees of freedom for the monoatomic, diatomic, triatomic, linear and triatomic non-linear cases. Now as you just saw, the monoatomic entities have a constraint of 0, diatomic ones have constraint value equals to 1, triatomic has a constraint value of 2, and triatomic non-linear has a constraint value of 3. So degree of freedom can be calculated using the formula F equals to 3n minus r, And so for monoatomic particles, degree of freedom is 3. For diatomic particles, it's 5. Triatomic linear particles, it's 7. And triatomic nonlinear particles, it is 6. Okay. So that is up to degree of freedom. That brings us to the end of this session. More sessions coming up.